Welcome to this tutorial. In this tutorial, we do Aspen Plus simulation of a regenerative ideal Rankine cycle with an optimized closed feed water heater. Just to recap, we previously discussed the closed feed water heaters that are used in regenerative cycles. We mentioned that the uh, steam is extracted from the turbine and is transferred to a heat exchanger. In this heat exchanger, the heat is transferred from the extraction to the feed water that goes to the boiler. After that, this extraction is condensed and is transferred either back to the condenser or if you have more than one feed water heater, you can use it somewhere else. But in this scheme, we only have one closed feed water heater, so that steam is transferred to the condenser, and we have a throttling valve here in order to drop the pressure to the same pressure of the condenser. As we previously mentioned, ideally the feed water is heated to the exit temperature of the extracted steam, which leaves the heater as a saturated liquid at the extraction pressure, which means that state 3 here is very close to a saturated liquid temperature. Uh, let's review one more time the example that we had before. Let's say if the extraction pressure of the turbine is 5 bar here, uh, this is stream number 5. If the pressure of stream number 5 is 5 bar, this means that the saturation temperature at 5 bar according to steam tables is 151.8. So if the feedwater inlet temperature is 50 degrees C, in an ideal closed feedwater heater, the feedwater leaves the closed feedwater heater state 3 at 151.8. This means that the feedwater is heated from 50 to 151.8. In reality, however, we use two parameters. In the design of a closed feed water heater, those parameters are TTD and DCA. The terminal temperature difference, or TTD, and the drain cooler approach, or DCA. These two parameters are important for evaluating the efficiency of the feed water heater and steam power plant. Both of these parameters help to optimize the heat recovery, determine the size of the heat exchanger, and improve the overall plant efficiency by reducing fuel consumption and operational costs. Let's start with the TTD. As I mentioned, it stands for terminal temperature difference. TTD is the difference between the saturation temperature corresponding to the pressure of the extraction and the exit temperature of the closed feed water heater. This means that let's say that we have the closed feed water heater like this. So the temperature of the saturation at extraction pressure is this value, and the feed water heater outlet temperature is this value. So the difference between these two is called TTD. The TTD is generally about 3 degrees C, but it may be as high as 5 degrees C. Uh, let's say that we have extraction at a pressure of 10 bar. At 10 bar, the saturation temperature is 179.91 degrees C. And let's say that the feed water inlet is 90 degrees C and the outlet temperature is 170 degrees C. This means that the TTD, which is the difference between the saturation temperature here at 10 bar and the output temperature of the feed water heater, 170 degrees C, is equal to 9.91 degrees C. A TTD of 9.91 degrees C means the feed water is heated close to the saturation temperature of the extracted steam, showing efficient heat transfer. The drain cooler approach, or DCA, on the other hand, is the temperature difference between the drain water that leaves the closed feed water heater and the feed water inlet temperature. DCA is generally about 5 degrees C, but maybe as high as 10 degrees C. So for the same example, if we have an extraction at 10 bar with a saturation temperature of 179.91, and this extraction goes to a closed feed water heater, the feed water inlet temperature is 90 degrees C, the feed water outlet temperature is 170 degrees C, and the drain outlet temperature is 140. In that case, DCA is 140, which is the drain outlet temperature, and 90 minus 90, which is the feed water inlet temperature, which is 50 degrees C. A DCA of 50 degrees C indicates how much cooler the condensate is compared to the incoming feed water, and it shows how effectively the heat exchanger drain cooler section is performed. Now let's do this exercise together. Consider a steam power plant operating on the ideal regenerative Rankine cycle with one closed feed water heater. Steam enters turbine at 15 megapascal and 600 degrees C, and is condensed in a condenser at a pressure of 10 kilopascal. Now we want to find the optimum amount of the extraction from the turbine at a pressure of 1.2 megapascal using TTD and DCA approach. The steam flow rate is 10,000 kilogram per hour, and we know that the saturation temperature at 1.2 megapascal is 188 degrees C. In the previous video, we extracted 20% of the steam from the turbine. Now we want to find the optimum amount. This is the difference. I will start the Aspen file that we did together in previous video, and then we take it from there. Here is the simulation that we did together in the previous video. We added the closed feed water heater to an ideal simple Rankine cycle. If you don't know how to do it, please watch that video first. If you look into the temperatures here, the feed water output temperature is 159, and we know that the saturation temperature at 12 bar or 1.2 megapascal is 188. So this means that this is not an ideal closed feed water heater. And if you calculate TTD, the TTD is 29. This means that we are far above the 3 or 5 degrees C, which is the typical value for TTD. So we need to manipulate the fraction here in order to reach a TTD of around 3 to 5. And if you also look into the feed water input temperature, which is 51, and then you compare it with drain temperature, 188, you see that we also are far above the proper DCA value, which is 5 to 10. So here in this case, 188 is the temperature of the drain, minus 51, which is the temperature of the feed water in. The value for DCA in this design is 137, which is not optimized. Now let's try to optimize this closed feed water heater together and see how the temperatures and the thermal efficiency will be affected. For the DCA parameter, what we can do is that to change the settings in the closed feed water heater. If you double click on the closed feed water heater, there is an option that is called uh, uh, hot inlet and hot outlet and cold inlet temperature difference here. This one. So hot outlet and cold inlet. So this is hot outlet drain temperature. Cold inlet is feed water in. So this is exactly the definition of a DCA. So we can set that value. Let's say that we put that value to let's say 10 degrees C, and then we reset calculations, and we rerun it just to make sure that it works. Now the results are available. Now you see that the temperature difference between the drain and the feed water in is 10 degrees C. This is what we wanted to do. Let's briefly check how the uh, results for the calculator is changed. You see that now the efficiency is 34.3 compared to 33.1% that we had before changing this parameter. Now the DCA is fulfilled. Now we want to also look into the temperature difference of the feed water out and the saturation temperature. What we can do here is similar to what we did for an optimized open feed water heater. We can go to the flow sheeting options and use the design specification, design spec. Here we make a new design spec, and in the input we need to define the variables. What is the specification we are looking for and what do we want to vary in our design. So what we want to do is to vary the fraction here, extraction fraction, until we reach a temperature difference between this stream and 188, which is the saturated temperature at 12 bar. And we can set it to like 3 to 5. So what we do is that first we define the temperature of this stream for the program. So here, click on new, temperature of closed feed water heater out. It's a stream variable, and we need to pick the stream variable, close feed water out, and temp. This is temperature. So a specification is 188 minus the variable that we have. You can right click and look into the variable list. When you have several variables here, it's very likely that you make typo errors. So you just copy and paste this, make sure that you don't have any typo in your simulation. So 188 minus the temperature of the closed feed water heater out. TTD, we said that is between 3 to 5. Let's say we take 3 as a target and the tolerance of 0.1. What we want to vary is a block variable. The block is splitter, and we are aiming to manipulate the fraction, flow fraction, for the extraction between 1% up to 50%. We reset the calculations and we rerun the simulation and we wait for the results. Now results are available. Now you see that we reached a temperature of 185. So this TTD is reached, and this DCA is also around 10, which is good enough. And we can look into the result for our design spec. You see the value for the stream is slightly changed. It's around 20.1%, slightly changed. And we also can check the results for the efficiency. Efficiency is also slightly improved. So now you can say that we have an optimized closed feed water heater regarding to a DC of 10 degrees C and TTD of 3 degrees C. For the second example, we have the same setup basically, a pressure of 15 megapascal and 600 degrees C for the superheated steam that comes to the turbine. But this time we want to find the optimum pressure for the extraction. So we don't have that pressure, and we want to find the optimum amount of extraction for that optimum pressure that gives us an optimum design or the highest efficiency. We want to again use the TTD and DC approach, and we have the steam flow rate. Let's see how we can do this in Aspen. Starting with the previous simulation, what we need to do is that we need to change the discharge pressure of the turbine number one using the DCA and TTD approach and see where do we get this the highest efficiency in this ideal cycle. Since we are varying the pressure, discharge pressure of turbine number one, this will affect the temperature, the saturation temperature, because at any given pressure, we have a specific saturation temperature. So if you change this from 12 to 10, then you have a new saturation temperature, which means that the design specification we define for the program needs to be modified a little bit. I will show you how we need to do that. We also need to add a cooler and heater here in order to reproduce saturation temperature automatically every time. I pause the video, I add this cooler and heater, and then we take it from there. Okay, now I have added a cooler and a heater. I showed you in the previous video for the optimizing open Feedwater heater how you use this, but just to recap, what we do here is that we remove the heat from the superheated steam that goes out from turbine number one. We make it saturated, and then we put the heat back to this stream. So basically, there is no difference between the state between stream T1 out, turbine one out, and split in. So there is no difference here. What we do is we just add these two cooler and heater here to do a trick and have automatically generated saturation temperature at the given pressure of the outlet of turbine number one. We click on the next. This is for the cooler. For the cooler, we need to set the vapor fraction to 0 and pressure drop to 0. So what happens is that the heat is removed from this stream until it's a saturated liquid. And then we put this back. So if you click on the next for the heater, since the heat is connected here from cooler to heater, you see this energy stream. So you only need to set up the pressure drop to 0. And that's it. So when you run this simulation, automatically you will see the temperature of saturation at any given pressure here in the output of the turbine number one. In this case, it's 12 bar, and at 12 bar, we already know that it's 188. So now we have this information. It's now I show you how to modify the splitter. I mean the design spec that we wrote for the splitter. Here we need to define one more uh, uh, variable here, and that's the temperature of the uh, reference uh, stream here. This is the reference stream. Maybe it's better if I change the color for this stream. So here you have the stream color and style. I put it to red so you can see here. So this red stream is where you can read your reference temperature, which is the saturation temperature at the given pressure of turbine number one. So we go back to the design spec input. Tref should be streams, stream variable. It's stream name reference, and the variable is temperature. So instead of 188, now we can rewrite this and write the tref. So I double check the typo, the spelling here to avoid any typos. So now we vary the fraction until we get a temperature difference between Tref and T close with water out equal to 3 with a tolerance of 0.1. We rerun the simulation just to double check that it works properly without any errors. Yes, the results is available. And now you see the temperature difference, or the TTD, between these two streams is 3 degrees C as we said it before. Now we need to optimize and find the optimal pressure or discharge pressure of turbine number one. We can do this in two different ways. One way is to perform the sensitivity analysis, as we did before for open Feedwater heater. If you don't know how to do it, please watch that video. In the sensitivity analysis, we try to change the discharge pressure of the turbine number one, and for each pressure, we calculate the efficiency, and then if we look at the diagram for the discharge pressure versus efficiency, and we go for the maximum in that diagram. The other option is to use the optimization tool here. As you can see in model analysis tools, you can click on optimization and you can create a new optimization. I will perform the optimization for this simulation. The sensitivity analysis, you already have one video that you can check. Uh, Here you need to define the variables for the program, the objective, and the vary is what we want to manipulate. So the objective is to maximize the cycle efficiency. We want to manipulate the output temperature of turbine number one, the discharge pressure here. And the variables that are involved are those variables that are involved in calculating the efficiency. So I can easily copy and paste those variables from the calculator. So I copy those variables. I go to this optimization and I paste them. Then for the objective, I also use the same equation. We want to maximize the efficiency, and the efficiency is calculated using this equation. So here we click here. So we want to maximize this equation. And in vary, we need to change the discharge pressure of the turbine number one. So it's a block variable, turbine number one. It is press, which is the pressure. We also need to set the lower and upper limits for this optimization. Let's say we investigate a range between 5 to 15 bar. If you're thinking about a specific step size, you can specify it here. Otherwise, that is fine. So we have all the input we need. We reset the simulation and we rerun it and wait for a few seconds. Results are available, so we go to the optimization results here. In the summary, you will see a list of the variables with the values that is prepared, and here the objective function value here is the maximum efficiency that has been calculated by the program. It's slightly higher than what we had before, and the reason is that we can check the pressure. The pressure is 12.01 bar, so the optimum pressure is very, very close to the initial value that we had in our simulation. The optimum pressure is 12 bar or 1.2 megapascal, and then the value that you get is 34.38% as the efficiency of the cycle. We also check all this temperature, pressure, and mass flow rates just to make sure that everything looks fine. Uh, the pressure is 12 bar, so the saturation is 100, temperature is 188. We have a good TTD. DCA also works fine. Almost, if you look into the flow rates, almost 20%, 20.1% is extracted and sent to the closed Feedwater heater. So everything looks okay. Thank you for watching this video, and I will see you in next video for more simulations. Thank you very much.